Alright guys, welcome to lesson 7.6. We're going to talk about integration with respect to y today. So let's go ahead and start off with some review here. Let's say I wanted to find the area under this curve. Well, from here to here. Now I know we could just use geometry for this, but I don't want to use geometry. I want to use calculus really quick. So here's my function. All right. We'll call it f of x instead of y, just for our purposes here real quick. So what we would do is we want to integrate this function, f of x, with respect to x, starting at x equals 0 and ending at x equals 6. And that represents the area under the curve, starting at 0 and keep going over to the right until we get to 6, and that's the area under the curve. Okay, so we could do that, and that's what we've always done. I want to show you guys a different way we could find the area under this curve. Instead of integrating with respect to x, we could do it as if we're integrating with respect to y. So the first thing that I'm going to do is I want to rewrite this equation first of all. Instead of having a function where y is a function of x, I want to rewrite this where I have x as a function of y. And all we have to do is we just have to get the x by itself. So I'm going to start by minusing 3. And then I'm going to multiply everything by -2. And I get that. So I've rewritten my equation now. I've changed it into it's really the same equation. I just rewrote it. So that instead of having the y by itself, I've got the x by itself. But now that means that I've got x as being a function of y. So I'm going to call this new function here f of y. It's literally the same function as the last slide. It's been rearranged so that instead of having a function where my input is x and my output is y, with this way, my input is y and my output is x. But they would give you all the same points, I promise. We just rearranged the equation a little bit, and I rewrote it as a function of y. So now if I wanted to find my area under the curve, I would be integrating a function of y, which means I would need to do it with respect to y, which means that my limits are going to be different. Instead of going from x equals 0 to x equals 6, we're going to go from y equals 0 to y equals 3. So in other words, instead of integrating from left to right, we're integrating from the bottom up. But you would literally get the same answer. So integration with respect to y is about integrating up, whereas integration with respect to x is about integrating to the right. You start here and you work your way to the right. But with y, you start at the bottom and work your way up the x-axis. But either way, you're just finding the area. You're going up, and as you do, you're tracing up the area and finding the area of the curve. All right? But it would literally give you the same answer. So if you were to calculate this, and if you wanted to on your calculator, you could do that right now. If you wanted to do that, and then compare that answer with this answer, I think it was +3, wasn't it? You would find you get the same exact answer. It's just that we're doing one with respect to x, and we're doing the other one with respect to y. So there's two main differences. One is that when you're doing it with respect to x, your function has x's in it. And the second difference is that the limits are x values. The endpoint on the left and the endpoint on the right. When you're doing it with respect to y, your equation has only y's in it, and your endpoints are the lowest point and the highest point, not the left and the right, but the lowest and the highest from top and bottom. Okay? And that's integration with respect to y. Now, when I'm talking about rectangles here, what I mean is that, you know how we estimated areas under curves using rectangles like this. You don't really need to know this too much at this point in time. Well, when you're integrating with respect to y, instead it looks like this. You're estimating here, you could estimate areas with rectangles again, but your rectangles are going to be horizontal instead of vertical. But that's kind of unnecessary. You don't need to worry about that too much. All right, so why integrate with respect to y? Well, one reason is because it's easier. For this one, you would need two integrals. For this one, you would need only one. Okay, so the one on the left, you'll probably understand it a little bit better because you're a little bit more used to it. But basically, what we would have to do is we'd have to find out where these two functions are crossing first, and that's at a. And we would have to set one integral up from 0 to a, and that would be the area under the f of x curve. But after a, we're looking at the area under the curve of g instead. So from a to c, I would have to find the area under the g function, and then I could add those two things together. But over here, since the g function is greater than the f function, we could write an integral like this instead, g minus f to find the area between these two curves, starting at 0 and ending at k. And notice I'm using the y-axis for my limits this time because we're integrating upwards. So we find the distance between g and f, and as we trace that up, as we integrate upwards, it traces out the area from 0 all the way up until we get to k right here. So it can be easier. So there are some cases where if you tried to do it with respect to x, you would have to write two separate integrals, whereas if you did it with respect to y, you could be done with one integral. So it could be easier in that respect. That's one reason. Another reason why we might want to integrate with respect to y is because sometimes instead of asking you to find the area between a function and the x-axis, sometimes they want to find the area between a function and the y-axis instead. And in that case, you're going to want to do a vertical integration, starting from here and ending here with your function there. So we could put some letters on here really quick just to make sense of this. So we would be integrating the g function with respect to y from a to b. And in this case, my a and b are y values, right? So sometimes instead of wanting to find the area between the curve and the x-axis, you might want to find area between a curve and a y-axis. And that's another situation where you'd want to integrate with respect to y. So there's two situations. One is because it can make some integrations easier. So instead of having two separate integrals and adding them together, you could just have one. The other reason is because maybe you're integrating to find the area between a curve and a y-axis. So those are the reasons why we want to learn it. And so let's review really quick. You guys might remember that if you want to find the area between two curves, you're going to take the function on the top and subtract from it the function on the bottom, so f of x minus g of x, and you integrate from a to b, whatever endpoints you want it to have on the x-axis. Well, the same thing is true when you're integrating with respect to y, but let's review this really quick before we move on to the y things. When f of x is greater than g of x, you could tell because f of x is above the g of x. So when you look at this, f of x is greater than g because it's above it, right? It's higher up than the g function is. But when you're integrating with respect to y, it's a little bit different. Same formula, okay? I want to point out a few differences though. We're going from C to D, and notice that those are y values. You should already know that. We've been talking about that. So in this case, we're starting at C and we're working our way upward as we integrate to find the area, right? The other difference I want to point out is this. How do you know when you're looking at functions with respect to y, which one's greater? When you're looking at functions of y, the one that's on the right is the greater, the one that's on the left is the lesser. So in this case, the f function is on the right, and it's to the right of the g function. And therefore, that means that the f function is greater, and so you write it like this. Now, once again, the same rule applies here as yesterday. So if we're using graphing calculators, which we are, it's really not too important if you just put absolute value bars here. It doesn't matter which one you put first. It'll get you the correct answer either way. The only difference between this answer and the other one, if you reversed it, would be that they come out to be opposite signs. But just put absolute value bars on it and you're good to go. But I do want you guys to be aware of the fact that when you're dealing with functions with respect to y, the one that's farther to the right is the greater function. That'll be helpful when we get to doing these kinds of things by hand. All right. So here's an example of area with multiple crossing points. So as you guys can see here, we have the red function is farther to the right than the blue function from A to B. So all the way from y equals A to y equals B, the red line is farther to the right than the blue. So from A to B, it would have to be the red line, which I'm going to call G, minus the blue line. But after they cross in here, from y equals B to C now, the blue line is farther to the right than the red line. And so from the interval from B to C, it's F minus G. You might want to label your graphs on your notes, just so, because I didn't do that. I meant to do that, and I forgot. So the red one's G and the blue one's F. But once again, if we're doing it on a calculator, all we really care about is what is our lowest point and what's our highest point. And since this and this are exactly the same with the slight difference, they're just opposite signs, by putting absolute value on it, it eliminates that difference, and you can put those two integrals together into one. So you really only need to integrate from A to C with an absolute value on there. Okay, so that's how we'll be handling the ones that can cross multiple times. And in fact, this is just how we're going to do all of our problems today. So let's do this one here. We have two functions. Now notice that these are functions of y. Instead of being y equals something, it's x equals something. Now, notice this one has a x equals a y squared, so that's going to look like a sideways parabola, right? Because you guys know that whenever you have a square, it's a parabola. But since it's with respect to y, it's going to look like a sideways parabola. So this is that one. And then the cubic one will be the other one. I guess I'll trace that one in green. The cubic one is the one that looks kind of like an N shape there, if you will. All right. And I want to find the shaded area there. I want to find the shaded area. All right. Now, I'm going to make this a little bit harder than it needs to be, and trust me, we'll make it easier as we go. So, first of all, I need to break this up into two pieces. I've got this piece on the bottom, and then I've got this piece on the top, and I have to treat them separately if I pretend I'm just doing it by hand. Okay? So for this first interval, where does it start and where does it stop? Well, it starts here and it ends here. But remember, we want the y values. So my starting point is -2, and my ending point is 0. And in that case, let's call this one x1 and this one x2. In this case, my red line is the one that's farther to the right. In other words, the squared one. So that's going to be x squared, the red one. The x squared function is to the right, sorry, the y squared function is to the right of the cubic one in this case. Okay? So it's going to be x2 minus x1. And remember, this is with respect to y. And you guys might be confused. You say, Mr. Bailey, why are there x's in there? I thought this was with respect to y. Well, they're calling these functions x's in this case, which is fine. They could have just as easily called them g of y and f of y, which I would have preferred, but it's fine the way they have it. We'll just leave it like that. So then we're going to do the next area. Now the next area, the one on the top, this piece. Where does that area start at? What y value does it start at? Well, it starts off at 0. And where does it end? About, looks like y equals 3. In this case, which one is farther to the right? On this area up here, which one is to the right? The green function or the red function? Well, in this case, it's the green function, which is the x1 function this time, minus the red function. Now, we're not going to really solve it this way, though. Okay, but I just want to show you how you would have to set it up if you were doing this by hand. Okay, which is a possibility. We're just going to make it a whole heck of a lot easier on ourselves, though. I'm going to call that one x2 and that one x1. The easy way to do this now is on a calculator. All you need is your very first starting point and your very last ending point. So from -2 to 3, just put some absolute value bars on there. And you can just go straight from beginning to end. You don't need to split it up and worry about which one comes first. And that's how we're going to be handling most of our problems today. Now, our calculators don't do things like this. They don't do functions of y. Okay, they only do functions of x. But it doesn't matter. We're just going to treat it like x. So when I type this into my calculator, -y cubed plus 6y, I'm just going to make the y's equal to x. It doesn't matter. You'll literally get the same answer anyway. It's just you're changing the variable. Your graph would not look the same if you tried graphing it, but you will get the same exact answer. So we're going to call the first one there x1. I think I changed my mind, didn't I? I think I said I was going to call that x2, but I guess I'll switch it to 1, and that one's going to be x2. And then the next one down is going to be -y squared, or in this case, -x squared. Okay? Now, I'm not going to graph it, because if you graph it, it's not going to look like this. It'll look something like that. Matter of fact, what it'll look like is something a little bit like this. If you were to flip it like that and rotate it like that, it would look like that. Want to see? We don't really need to look at this, but just for the heck of it, I'll show you. That's the difference between switching your x's and y's. It's like you flip it and rotate it. The graph, other than that though, the graph looks exactly the same. So you're really going to be finding the same thing. It just looks different, that's all. But we don't care about the graph. Let's get out of there. All right, so what we want to do is we want to integrate from -2 to +3. So here we go. We're going to do math, 9, -2, +3, and we're doing absolute value, right? And the order doesn't matter which function you put in there when you have those absolute value bars. And you're good to go. Once again, absolute values make your integrals think a long time, but there's our answer, 21.083. Okay, so you don't have to do what I did at first, where I rewrote it as 2 separate integrals. I was just kind of talking about stuff. All I want you guys to do is do what I did here in the calculator and find the area. So let's have you guys try one. Homework problem number 1. Pause the video here, and when you unpause it, you will see the solution. That looks like the same answer I got on my problem. That's kind of strange and a little disappointing. But what's important is, did you guys realize that the bottom number is -3? Because the lowest point is right here, and that y value is -3. And the highest point is right here, and that y value is 2. And we're going from -3 to +2. And you put your y2 minus y1, which is really x1 minus x2 in there. But you end up with 21.083. Okay, so that's one question. Let's do another one here. What about if I wanted to find the area between a curve and the y-axis? Well, the y-axis actually has an equation to it, believe it or not. the equation of the y-axis is x equals 0. Okay, so we'll call that our x1, and we'll call this one here our x2. Okay, so instead of f of y, I'll put x2 because it'll look a little bit more familiar on our calculator that way. So let's do a little color change here. Actually, let's change the x1. I'm going to do green on that. All right. Well, right here is the y-axis. That's x1. All right, and then we have x2, which is this parabola. Now, we're going from what to what? From y equals 2 to y equals 6. And we would typically do the function that's farthest to the right, which is x2, minus the function which is on the left, which is x1. But if you just put absolute value bars on there, you're going to be safe, and I would recommend you do that anyway. And so that's basically it. So if you ever want to find the area between a function and the y-axis, then that's how you would do it. Just think of that y-axis there as a 0, as x equals 0. Now in that case, since this is 0, really we can kind of simplify this, right? x1 equals 0. Well, x2 minus 0 is just x2, right? Now, if you want to find the true area under the curve, leave the absolute value bars on there, because that'll make sure you're always looking at positive. But do remember that as soon as your function goes past the y-axis, let's say I had this. Well, this area would be positive, but this area would be negative because it's to the left. So anything to the right of the y-axis will be positive. Anything to the left will be negative. Same thing like whenever we did the x-axis ones, right? Above was positive and below was negative. Well, whenever you're doing y-axis stuff, anything to the right is a positive area, and anything to the left is a negative area. But if you don't want these things to cancel each other out and you want to just know what's the true area, then put absolute value bars on there and it will make that positive and you end up with the total answer. Okay, but if you want to just kind of keep it easy and just always try to remind yourself to to write it out like this, you can. It doesn't really matter. But we can go ahead and work that out now. So here we go. We go to y equals. We're going to call our first function there negative y squared plus a y minus 12. My second function, I'm just going to call it 0. And then we're going to get out of there and we're going to do math 9. And we're going from negative 2. No, it was a positive 2. Fix that. There's no negative there. Positive 2 up to 6. And we're just going to do y2. Actually, we want to do absolute value first, just to make sure we get the true area and we don't get negative areas cancel each other out. Although this one wouldn't have any negative areas because it's all to the right, but just as a good habit. And we're going to do y2 or y1 minus y2. And since it's absolute value, the order doesn't really matter. And we end up with 10.666. So there you go. So that's basically it. If they ever ask you to find the area between the curve and the y-axis, if you don't mind counting the negative area, over here is negative and this is positive, then just put the function in the way it is. But if you want it to become all positives, then just absolute value it. And that's the true area between the curve and the axis. So here's a homework problem. So now for you, I don't want you to have this side be positive and this side be negative. I want the whole thing to be positive. So when you do set this up, absolute value bars on it, okay? All right, so go ahead and pause the video here, see if you guys can find the area, and you'll be good to go. All right, so long ways to say, okay, I want to go to the x-axis, right, which is, I'm sorry, y-axis, which is here. So I'm going to stop at 2 and start at -3. And then we're going to call this x1 and subtract from it the equation of the y-axis, which is 0, and put an absolute value on there, right? You could do that. Or since it's just 0, you can just get rid of that 0 and just do the function itself, right, from -3 to 2. And so that's what we'll do on this one. So when I do it, since I'm not even going to include the 0 because it's just a 0, I'm just going to put the function in x1 only there. But if you did include the 0, it's not going to be wrong. It's just unnecessary button pushing, kind of. Okay, so now we're going to do our integral. We're going from -3 because that's the lowest point where the blue line touches the y-axis. We're going to go up to 2 because that's the highest point where the blue line touches the y-axis. We want the true area. I don't want that area to the left to be considered negative and the area to the right to be considered positive. I just want to make them both positive so I can find the total area and ignore the sign. So we're going to do absolute value. And it's going to be of my function that I just typed in, which is y1. And we get dx there. And we're good to go. Oh my gosh, I got 21 this is not a very creative software program that I have. I keep getting 21.083. Ugh, I hate that. All right. Anyway, that's it. That's the answer, as repetitive as it may be. All right. Let's go and take a look at one more concept before we call it a day here. Let's review the formula of an ellipse. The h and the k in this formula represent the center. The A, I'm going to call it the x radius. That's not what it's really called, by the way, but it'll work for our purposes today. I'm going to call it the x radius, and I'm going to call the B the y radius. What an ellipse is basically kind of like an oval. It's an elongated circle. So whenever you have these things, you're going to have a center at coordinates h, k. And then what you're going to do is you're going to have a radius that goes in the direction of the x, and that's the a value. You're also going to have a radius that goes in the direction of the y, which is the b radius. And then you're going to go ahead and connect that, and then you can kind of complete a similar, just using symmetry, you can kind of get the rest of the circle or ellipse that way. So there you go. That's an ellipse. So the h and the k represent the center. The square root of the number on the bottom of the x tells you the x radius, and the square root of the number on the bottom of the y tells you the y radius. And that's going to be good enough for us to kind of be able to get a picture out of all of this. Now, what we're going to be needing to do, though, is we're going to be needing to get one of those variables by itself, either the x or the y, in the problems that we're working on today. So let's go ahead and take a look at a problem here. So let's say I wanted to find the area in the ellipse. So I'm going to put some steps on here for this process, but basically what we're going to do is we're going to be using a process of integration to find the area of an ellipse. So the first thing that we're going to want to do is we're going to want to graph the ellipse. Okay, so my h is 4. I have no k. And you're going to do the opposite sign. In this case, you're going to do the opposite sign of both the h and the k. So in this case, our center will be 0, 4. I'm sorry, I take that back. It's 4, 0. And then my x radius, if I may call it that, it's going to be the square root of that number. It's going to be 4. And my y radius will be the square root of the number underneath of the y, which is 2. So let's see what that graph would look like. I'm going to start at 4, 0. And my x radius is going to be 4. So from the center, I'm going to go out to the right 4 spaces and to the left 4 spaces. And my y radius is going to be up 2 and down 2. So I don't think that was very evenly spaced. Let me do that again. Still not very good, but oh well. All right, so up 2, down 2. And then we're going to go ahead and connect those 4 outer dots. And we have our ellipse. Okay. Now the next thing we're going to do is we're going to solve for one of the variables. Either x or y. Now if you solve for x, which means if you get the x by itself, your integral is going to be with respect to y. But if we solve for y, your integral is going to be with respect to x. Okay, so now on mine, I'm going to choose to solve for the y. And since I'm solving for y, my integral is going to end up being with respect to x, and you'll see that in a moment. But why am I choosing to solve for y? I just think it's a little bit easier to get the y by itself, okay, in this case, because it has less stuff with it. Now, on your problem, I would encourage you to get the x by itself, so you are going to have a practice problem after this, and my advice would be for you to get the x by itself, so your integral will be with respect to y. But for now, how do we get y by itself? Well, the first thing we're going to do is we're going to minus this entire fraction on both sides. So now that's gone, and on the left side I'm left with y squared over 4, and on the right side I've got 1 minus that fraction I just subtracted. The next thing is if there's a denominator underneath of that y squared, we're going to multiply everything by 4. So times 4, times 4, times 4. And in this case, these are going to cross off. And this can reduce the 16 to become 4. And that's going to leave me with y squared equals 4 minus this. And then the last thing we're going to do is we're going to take the square root on both sides. Now something you have to remember is that when you solve for a variable by taking a square root, you get a plus and a minus, and that has some significance that we've seen back when we were graphing circles, and the same significance applies to ellipses. Okay, so when you have a y equals ellipse, right, the positive part, the positive square root, refers to the top half of your ellipse. The negative square root refers to the bottom half of your ellipse. Same thing with circles, right? But it's going to be a little bit different when you guys do your problem because you're going to be solving for x. So you're going to have an x equals ellipse. And when that happens, a positive square root means the right side of the ellipse, and a negative square root means the left side of the ellipse. Okay, so just bear that in mind. And there we go. So basically what we have then is we've got two halves of this ellipse. I've got the top half, And that top half is the equation y equals the positive square root of 4 minus x minus 4, sorry, x minus 2 squared over. Oh, why did I change that? This thing was supposed to be a 4 the whole time. My bad. I'm going to rewrite that though so it looks a little bit nicer. For some reason I changed my 4 into a 2 along the way. I'm not too sure why I did that. Blunder. Alright, so there's that. Now the bottom half of our ellipse though is going to be the equation y equals negative square root of 4 minus, same exact thing, it just has a negative in the front of it. Okay, so when you solve for one of these variables, it's going to split your ellipse up into two pieces where each function represents one of the halves. Okay, so now that we've got that, we're ready to do our third step, which is to set up our integral. Oops. All right, so I want to find the area in between these two curves, in between the pink curve and the green curve, going from x equals 0 to x equals 8. So here we go. Integral. How do you find the area between two curves? You do the top curve, which is, we could call it y1 if you want to, but I think I'm going to go ahead and actually just write the function in there, and you'll see why in a second. But technically, when you're doing this process, you could just put both of the functions into your calculator, the positive one and the negative one, and just find the area in between the curves like we always have. What I'm about ready to do, you don't necessarily have to do, but I just want to show it to you as a possibility. All right, so we do our top curve minus our bottom curve, which is the same exact thing, it just has a negative in front of it. And I'm doing all this with respect to x. Okay, now, like I said, in your calculator, if you wanted to, you could type this under y1, you could type this under y2, and just do it the way we've always done it. But there's a reason I'm deciding to write it as two separate functions here for now. I'll show you in a second. But we want to get our limits. Now remember, since I'm doing this with respect to x, my limits here need to be x values. So my lowest x value is 0, my highest x value is 0 and 8. Now, if you are integrating with respect to y, then you wouldn't be integrating from 0 to 8. Instead, you would be integrating from -2 to +2. You would be integrating in an upward direction if you had solved for the x instead and been integrating with respect to y. So but either way, you're going to get the same answer. Now let's talk about why I'm deciding to set it up like this instead of just treating it as two separate functions. Because really, these two things are exactly the same. The only difference is the green one has a negative in front of it. But look, the negative goes away because you have double negatives here in the middle. So it just becomes plus. And anytime you add something to itself, you get two of those things, right? That's all. So you just put big 2 in front of there, and you can put them together as one big integral. So that's an option. Okay? So you have two options for how you do your integral. You could either just treat them as two separate integrals and do it, or two different functions and do it like we've always done it, y2 minus y1, or you can do it this way where you just write the function and put a 2 in the front, because that's what it's going to turn into every time when you're doing these ellipse problems. Okay? And the same thing will happen with the dy. All right, so from here we're ready to go ahead and type it into our calculator. So let's go ahead and do that. So I've typed the function into my calculator, as you can see here. And then we're going to go to the home screen and we're going to do the integral of that from 0 to 8. Taking a little while, but we get an area of 25.133 approximately, so that would be our final answer there. All right, let's move on. Let you guys try one of these here. So here's homework problem number 5. For this problem, it's going to be easier for you guys to solve for x. I solved for y, but you're going to solve for x. And the result of that is that you're going to be integrating with respect to y instead of with respect to x. So let's go ahead and have you guys do step 1, though, which is to graph it. So pause the video here and see if you guys can graph the function. When you unpause it, you'll see the graph. All right, so there's our graph. Now let's go ahead and move on to step 2. I want you guys to solve for x. Get the x by itself. When you unpause the video, you'll see the solution. So this is what you guys should have gotten. Now, what I want you guys to do is I would like you to split your ellipse up into 2 pieces and label each half. Label one half as the positive square root and the other half as negative. And remember, this is an x equals ellipse. It's not a y equals ellipse. When you unpause the video, you'll see how I've labeled them. All right, so remember, when you're doing x equals ellipses, you split your ellipse in half. With the positive half being the positive radical, the left half being the negative radical. All right, we're ready for step 3. Now, I don't care how you guys want to go about setting up your integral. It's up to you. I'm going to do it the same way I did before, but go ahead and see if you guys can set up your integral. And what's really important is the limits. I want to make sure you get your limits right on this one. So there's our setup, but as I mentioned before, we really want to make sure you guys got the limits here. Did you do -1 and 5? Because remember, when you're integrating with respect to y, you start from your lowest y value to your highest y value. We're integrating in an upward direction between 2 horizontal functions. Right? Now, the simpler way to write this would be to put them together, as I said before, where you just put a 2 in the front because the double negatives become a positive. And then you're basically just adding 2 radicals that are exactly the same together, which means that you can just put a 2 in the front of it. Okay, and that's what we'll put into our calculator. Go ahead and pause the video here and see if you guys can calculate the value of your radical. All right, so here's how you would type it into your y1, and then here's how you'd set it up on your calculator to be integrated, and the final answer should be 9.425 approximately. And that does it. So that takes us to the end of our lesson. And so we'll see you guys next time.